Now that we've talked about finding means and variances and covariances for random variables, we're going to talk about taking linear combinations of random variables and being able to find the means and the variances for those linear combinations. So when we have a single random variable x, we have a theorem that says that if a and b are constants, then the expected value of a times x plus b is equal to a times the expected value of x plus b. Now, there's a couple of corollaries of this theorem, so these are direct results of this theorem. The first one is found by setting 0 as a, and when we do that, we end up with the expected value of b is just b. So the expected value of a constant is that constant, and if we think about that, that makes sense. A second corollary we arrive at by setting b as the constant 0, and we find that the expected value of a constant times our random variable x is equal to that constant a times the expected value of x. So all of that hopefully is fairly straightforward. Then we have a theorem that gets a little bit more into this, where we're looking at the expected value of the sum or difference of two or more functions of that single random variable x. So we have the functions g of x and h of x, and when we take the expected value of the sum or difference of g of x and h of x, that is actually equal to the expected value of g of x plus or minus the expected value of h of x. So if we're talking sums, we're going to be using plus in both places, and if we're talking differences, we're going to be using the minus sign in both places. Now, the sum or difference idea also works when we're dealing with two random variables, x and y. So if we have functions of two random variables, x and y, g of xy and h of xy, the expected value of the sum or difference of g of xy and h of xy is equal to the sum or difference of the expected value of g of xy and the expected value of h of xy. So again, we have a couple of corollaries or direct results of this theorem. The first one, if we let g of xy equal g of x, and we let h of xy equal h of y, then we see that the expected value of the sum or difference of g of x and h of y is actually equal to the sum or difference of the expected value of g of x and the expected value of g of y. Similarly, if we instead say g of xy is equal to x and h of xy is equal to y, then we see that the expected value of the sum or difference of our two random variables x and y is equal to the expected value of the random variable x plus or minus the expected value of our random variable y. Now we also have a result for the product of two random variables. So if we have x and y be two independent random variables, then the expected value of the product of x and y is equal to the product of the expected value of x and the expected value of y. Now there's a corollary of this that maybe doesn't feel as straightforward as some of our previous corollaries. So this corollary says let x and y be two independent random variables, then we have the covariance of x and y is equal to 0. Now, this doesn't necessarily seem like it's as straightforward directly from this theorem, but if we remember a theorem that we had previous about the covariance of two random variables x and y, where it equaled the expected value of x and y, the product, minus the mean of x and times the mean of y. And we remember that the expected value of x is the mean of x and the expected value of y is the mean of y. Then this tells us that when our two random variables are in fact independent, then the covariance is going to be 0. Otherwise, we might have something other than 0 when we take this difference. Now let's take a look at what the variance of a linear combination of random variables is. So if we have x and y, both random variables with a joint probability distribution f of x, y, and we have a, b, and c as constants, Then to find the variance of the linear combination ax plus by plus c, we actually take a squared times the variance of x plus b squared times the variance of y plus 2 times a times b times the covariance of xy. So there's some corollaries for this. There's actually lots of them. So the first one, if we set b equal to 0, then we find that we're taking the variance of the linear combination ax plus c, and that's going to equal a squared times the variance of x. And since there's only one variance in this equation, we don't actually have to write that subscript x, so we can just write a squared times the variance. Similarly, if we set a equal to 1 and b equal to 0, then we're actually taking the variance of the linear combination x plus c, and we find that that's equal to the variance of x squared, or just the variance squared. If we have b is 0 and c is 0, then we have the variance of ax is going to equal a squared times the variance of x, or just a squared times the variance. Now going a slightly different direction, if we have x and y are independent random variables, then the variance of the linear combination ax plus by is going to equal a squared times the variance of x plus b squared times the variance of y. Now, to wrap your mind around this, you need to remember that the covariance of xy equals 0 whenever x and y are independent. Carrying on with our independent random variables example, if x and y are independent random variables, then the variance of the linear combination ax minus by is also a squared times the variance of x plus b squared times the variance of y. And this is because b is being squared. So regardless of whether b is a positive or a negative number, or being added or subtracted, then it's being squared, and that's going to turn into a positive for us. Finally, if we have n independent random variables, x sub 1 all the way up through x sub n, then the variance of the linear combination a1 times x1 plus a2 times x2 plus all the way up to an times xn, then we have that is equal to a sub 1 squared times the variance of x sub 1, a sub 2 squared times the variance of x sub 2, plus, and adding those all the way up to a sub n squared times the variance of x sub n. Now you might notice that I've chosen to not include any examples in this video. The reason for that is we already know how to find the mean, the expected value, the covariance, the variance of all of these things. And so really what it comes down to is selecting the proper theorem or corollary for the linear combination at hand. Unfortunately, I don't think that watching me do that over and over again in examples is necessarily going to help you as much as taking a look at some linear combinations yourself and attempting to figure out what the proper corollary or theorem to apply is and trying it. And of course, we can talk about it if you run into any problems, but spend your time doing some problems.